Morning all. Today is obviously a very special day because we're going to finish the graphs booklet. So before we start celebrating, we're going to have a look at acceleration, speed, distance and time, which we started looking at yesterday with the speed time graphs. We're going to finish off today with the distance time graphs. So there's some formulas we should already know from chapter 9. We should know that speed is distance over time. We should have a general idea of this distance speed time triangle. But we should also be familiar with, or should know now, an acceleration triangle. I've said acceleration, change in speed and time. If you wanted to have that as a triangle, because you could, you'd have acceleration down here, you'd have change in speed on the top, and time on the base. Okay. So I've also made the point here that it's really important to look at your units before you do anything with it. So if we're talking about stuff like miles per hour and we had 1 hour 30 minutes, we'd want to change that to 1.5 hours, etc., etc. So let's use those two triangles to answer the questions that are in front of us here. We've got our first one. We want the speed. We've got 315 kilometers, and we've got that. So we've got a distance. We've got a time. If we want to do a speed, if we cover up the speed on our triangle, that tells us to do distance divided by time, and the time itself is going to be, it's 1 3/4 hours, so it's going to be 1.75 hours. So we need to do 315 over 1.75. That'll tell us 180. Make sure you look at the units. It was kilometers was the distance, per hour for the units. Okay. So that's the general idea here. We want to convert units to be hours, and we want to use the triangle to work it out. So, next one. We've got distance, we've got a time, and we've got a speed. The time, we want to, again, change this to fractions of an hour. This is 40 out of 60, or we could say this is 2/3 of an hour, and this unit doesn't need changing, kilometers per hour. Distance is equal to speed times time, according to our triangle. So that's going to be 63 times 2/3 gives us 42 kilometers. The next one, we want a time. This time it says it wants it in minutes. Our units are in miles and miles per hour, and that's fine. We can kind of work out the time first, then convert it, or we could convert this to miles per minute. But I think I'll stick with them at the moment. So we've got a speed, we have got a distance, and we have got a speed. Time is distance over speed, so that's going to be 36 over 20 equals 1.8 hours. If we want to convert that to minutes, we're going to need to times it by 60. That will give us 108 minutes. Or you could say 1 hour 48 as well, but it did want it specifically in minutes. So that's the distance speed time triangle. But we can also look at acceleration. Again, just to remind you, we've got acceleration, we've got change of speed, and we've got time. So we want the acceleration of a car that goes from 2 to 8 in 10 seconds. So acceleration is change in speed over time. The change in speed was 6, it went up by 6, and the time was 10 seconds. So that would be 0.6. Now the units of acceleration, the ones we normally use, are meters per second squared, or meters per second, because it's how much the speed is changing by per second. Anyway, so this is what we would expect to see. Next one, we've got the speed of a car that has accelerated at 4 from a starting speed of 3. So we're going to look at change of speed. According to our triangle, change of speed is equal to acceleration times time. So it's equal to 4 times 7. So it's equal to 28 meters per second. That's how much the speed has changed by. But we started at 3. So we'll end up at 31 meters per second. Okay? And our final one, how long, so that's a time question, does it take a train to decelerate from this at its deceleration? So this is our change of speed, is equal to minus 54, because it's decreasing from 54 to 0, and its acceleration it's a deceleration, so it's getting slower, is minus 10. And we want time. So again, according to our triangle, time is equal to change of speed over acceleration. So that would be equal to minus 54 over minus 10. That would be 5.4 seconds. Cool. So that's the general idea with the triangle. Hope that makes sense. We're now going to consider, to finish off, some distance time graphs and how we might use that. So, distance time graphs in general show us how distance changes over time. There's not really a non-stupid way of saying that sentence, I suppose. And what we need to bear in mind when we're looking at them is those two triangles we just considered about speed, distance and time and acceleration and such. And have a general idea that the gradient of the line gives you the speed. Quite important. So let's use that fact first. Here's Thomas's morning bike trip. He starts presumably at home, then he goes rapidly away from home to 40 miles away from home by 8:30, stays still until 10 o'clock, so maybe just stays at the place he went to, then goes back home slowly and then quickly. The steeper your line, the faster he's going to be going. So we're trying to find speeds, that's change in distance over time basically. So for A, it's going to be 40 miles is how far he travelled, and he took 1 hour to do it. That's from 7:30 to 8:30. So the speed was 40 miles per hour. That's a hell of a bike ride. Well done, Tom. For B, speed doesn't change at all, or distance doesn't change at all. Over I guess 1.5, but it doesn't really matter because we're going to get an answer of 0 for speed there. The gradient is 0. For C, it is a negative gradient, but we still say speed is positive. We don't have like positive and negative speed, so we can just think about change in distance. He went from 40 miles away from home to 30 miles away from home, so 10, and he did that in a time of 1 hour exactly. Yeah, from 10 till 11, wasn't it? So he's going 10 miles per hour during part C of the journey, and then during part D of the journey, 30 miles travelled, and we do it in another hour, so he goes home at a speed of 30 miles per hour. Cool. Okay, so let's look at anything else we can do with this. Here's a classic distance, speed, time question. Laura goes for a cycle from her house to the post office 4 kilometres away. How long does it take her to cycle to the post office? So we're going to have to assume the post office is here. So if we want to know time, and we have distance, we can just measure time by looking across the axes, can't we? So this is like 11:05 she starts at, and it ends at 11:20. So it would just be 15 minutes. Her speed cycling to the post office though, that's going to be our gradient, our change in distance over time. That's going to be 4 kilometres she travelled, and she did it in 15 minutes. So speed is distance over time, so 4, but we wouldn't do it over 15, we'd do it over a quarter, or over 0.25, because that's how many hours that represents. So her speed was 16 kilometres per hour. Distance is in kilometres here. How long does she spend at the post office? This amount of time. Looks like 20 minutes to me. And then we want to work out her speed cycling back home. So that's the last bit. Again, we'll do a gradient. That's a distance of 4 again. And that's a distance of 20 minutes. So 20 minutes, what would that be in terms of a fraction of an hour? That would be a third of an hour. So her speed going home is 4 over a third is 12 kilometres per hour. A little bit slower than when she came out. Now, as well as being able to interpret things from our triangles, from our graphs, we also need to be able to draw them. So the last thing we're going to look at is some sample journeys that we need to draw out. Again, if you think you know what you're doing with this, feel free to have a go and then look at my stuff to confirm, but I'm just going to go ahead with it. So we've got Erin leaving home at 11 a.m. So we'll start at 11. We kind of need to work out scales before we do anything. We know that the end of the journey is at 3 p.m. So this has to go to 3. And to me, it looks like I could use that each double square is half an hour, maybe. So each little square is 15 minutes. That feels like it fits. Cycles at a speed of 60 miles per hour for 90 minutes. So we want to work out distance here. So we've got distance and time we're doing. So distance is speed times time. So distance is 16 times time is 1.5. So she will have travelled 24 miles in that point. Then she stops, then she goes home. So we need to get up to 24 miles away. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, this only goes up to 20. So if we want to cover 24 miles, we need like each square to stand for maybe 2. So we go 10, 20, 30, 40 maybe. So for 90 minutes, so until 12:30, travels 24 miles. So we'll make a mark at 24, and we'll try and join that up with a reasonably straight line. This is obviously her going away from home. Stops for half an hour, so that takes you to 1 o'clock. And then travels home by 3 p.m. There we go. So there's our distance time graph drawn. What's Erin's average speed on the return leg? Well, as we've said on the previous page, your speed is equal to your gradient. So we'd want to find out, did it change in distance? Is 24 miles. Yep, we're in miles here. And your time is 2 hours between 1 p.m. and 3 p.m. So 24 over 2, she went home at 12 miles per hour. Okay, let's have a look at one more here. Got a helicopter this time, very exciting. Leaving Bristol at 10. Okay, so that means we're going to have to start at 10 for time. It flies for 45 minutes at 80 kilometers per hour. So again, we'll do distance is speed times time. And the time is 3/4 of an hour. So that'll be 60 kilometers. Then it lands for 30 minutes. And then it flies for another 65 kilometers. And then it goes back home at a certain speed. So the amount of distance we're going to need to cover is going to be 60 plus 65. We're going to need to go up to 125. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3. So we've got 20 squares to play with again. We could go with each square representing 5. Nope, we couldn't. That wouldn't fit. What should we go with? Let's just play it safe. Each square can represent 10. So 50, 100, 150 and 200. So how far along do we need to go? Well, we've got 45 minutes and another 30 minutes and another 30 minutes and then a journey home. So that's 75, hour 15, hour 45. We might need a few hours to get home, so let's do the same thing we did on the last one. I'm going to use military time. So that's 1 o'clock, 2 o'clock, 3 o'clock, etc. Okay, I think we're in a position to do this. So in the first 45 minutes, we need to travel 60 kilometers. Then in the next 30 minutes, we need to not move, so that'll take us to 11:15. Then in the next 30 minutes, we need to travel 65 kilometers. That'll take us up to 125 by 11:45. Let's try and draw a slightly straighter line than that. There we go. And then we go immediately home at 100 kilometers per hour. So we need to work out how long that's going to take. Time is going to be distance over speed. The distance is 125 kilometers and the speed is 100, so that's 1.25 hours or 1 hour 15 minutes. So we'll get home 15 minutes, 1 more hour at 1 o'clock. There we go. There's our helicopter's journey. draw a distance times graph to show the journey. Done. Complete. Okay, so that is /was graphs. Nice one.